Okay, let's. You said that from laws of motion we can start.
The conservation of momentum.
Okay, conservation of momentum. See, if I start, you can see the board now.
Yes, sir, I can.
Okay. So now let's start with the conservation of momentum. It's there in laws of motion only. You want me to do the numericals or the theory portion?
So can we start the theory portion, then do a numerical
Okay.
conservation of momentum?
Okay. So we are starting with conservation of
So it's
momentum.
after conservation of momentum, the third law of motion, right? We do.
Yes.
Okay, sir.
In conservation of momentum, what we have done? We have done that if the net, what is the statement of this? The statement says if the net external force, if the net external force acting on the system or body is zero, then the momentum of the system remain conserved. Okay, this is the statement. Statement you are getting what it means. What is the meaning of this statement?
Yes, sir.
See, the statement says if the net external force acting on the system or body is zero, then the momentum of the system remain conserved. This is the statement actually. Now, what we can see from here, from Newton's second law of motion, from Newton's second law of motion, what we can write from here? We can write Newton's second law of motion. What is the statement for this? The statement says the force, the external force is directly proportional to rate of change of momentum. This is what it says. The force is equal to rate of change of momentum, like this. Now, what if the external force is zero? This is what we are saying. If this is the external force, if this becomes zero in the above situation, what will happen? Let's say put 0 over here and we can write dp by dt is equal to 0. That means we have learned that differentiation of a constant is 0, isn't it?
Yes, sir.
Differentiation of a constant is 0. That if the force is 0, this momentum, this p becomes constant. So now it is constant. At constant means the momentum p represents momentum. If the momentum is constant, that means initial momentum is equal to the final momentum. Initial momentum is equal to the final momentum. This is actually the statement of the conservation of momentum. You got the basic idea? That is the basic idea is if the net external force acting on a body or a system is zero, then the momentum of the system remain conserved. That means remains same. So this is the statement actually. This is the meaning. Now, how we can say this thing? We know that force is equal to dp by dt, rate of change of momentum,
Yes, sir.
from the Newton's second law of motion. We
Yes,
know
sir.
this p is momentum. It's constant over here. P is actually momentum. Actually, it's momentum. And what we know, how we can write P is equal to m into v, mass into velocity. We know this thing. So initial momentum is equal to final momentum. Okay. So this is the basic statement of this. This is the basic idea. And what else we can do is, we can do some derivation also of this. You want me to do the derivations, other derivations in this?
So if it's very important, sir. I mean, for example, I can do it.
No, I don't think they were going to ask any such thing. For example, they will be asking numericals or those types of things, not much about it. For example, we can have, for a system of n number of particles, let's say. For example, you are having, there are many applications of it. For example, what are the applications? They can ask numericals about it. They will not ask the derivation. I don't think the derivation they are going to ask. The concept is important, and the next thing is important is numericals are important. They will ask questions about this. For example, two balls are colliding or two objects are colliding. Okay, after their collision, what happens? One object is moving with some velocity, on the other object is moving some other velocity. They may ask you to find the velocity of the other object. Or what they can ask? They can ask, for example, if a particle is there, if a bomb is there, let's say. They say ki if it explodes into two particles, they have given the velocity of one particle. They may ask you the velocity of the another particle. Likewise, if a gun is fired, a bullet is fired, the bullet is going in the forward direction, and the bullet and the gun will move in the backward direction. This is how they can ask. Okay, let's try to take an example of that bullet and gun using this conservation of momentum. Can we do it? We can, from there we can see how the velocity of the gun will be negative or in the opposite direction compared to the bullet which is moving in the forward direction. So we have written initial momentum is equal to final momentum. If we are having a two body system, what we can have, the next line we can write over here is, if we are having a two body system.
So, this concept can be applied to that a particle exploding to many pieces going off into
Yes.
different angles.
Yes, it can be used to application. It can be used, suppose a projectile is fired. A projectile is fired and in between it breaks into two pieces. And one particle is going with some velocity. They may ask you to find the velocity of the other particle. There also we can use this concept. We can use this.
What they give angles, sir?
Yes.
If they give what angle they
Yes, they can give angles also. For example, if a projectile is going like this, and at some point it is exploding into two parts. One is going like this, another is going like this. In that case, what we will have to do, we have to conserve this momentum along x-axis and y-axis. Are you getting this thing? Initial momentum is equal to final momentum. We know momentum is a vector quantity. This momentum is a vector quantity. We know this.
Yes, sir.
So when it is a vector quantity, there is a requirement. For example, the one particle is going like this. The other particle may go like this or somewhere else. Let's say other particle will go like this. So what we will have to do, we will have to do the conservation of momentum. For example, particle going like this, we can make two components for it. One component along this direction, one component along this direction. This particle is going like this. Again, we will be making two components, one component along this, one component along this. So what will happen? We have to conserve the momentum along x-axis and along y-axis. You have to make the component of the momentum along x-axis and y-axis, and then we have to conserve them. Then we can find the solution to such types of problem. Okay. So this is one thing. And from here we have seen that initial momentum is equal to final momentum. That is, if we are having a two particle system and if we are conserving their momentum along, let's say, x axis or y axis, how we can write? We can write like this: m1 u1, where m1 is the mass of first particle, u1 is the initial velocity of first particle. Then we can write m2 u2, where m2 is the mass of the second particle, u2 is the initial velocity of the second particle. So this is the initial momentum of the total system, because we are having only two particles in our system, and this will be equal to the final momentum of the system. Finally also we are having two particle system in our momentum. The mass, if we are considering the mass remains same, m1, its velocity will become v1, final velocity. We are considering the mass is remaining same, and this is how it is. There may be a chance that mass may also vary. Okay, so this is how it is. While moving, the mass can also vary, but here we are considering the mass is same. If the mass is varying, then this m and m2 will also vary. That we can put the value, but the momentum will remain conserved. And moreover, this conservation of momentum can be used in collision. Wherever there is a collision, one object is coming and it is colliding with the next object. While it is colliding with the next object, then they may ask anything about that. There also we can use this conservation of momentum. All type of collision. See, in all type of collision, what happens? Momentum, total linear momentum, conserve before collision, during collision, and after collision. The momentum remains before collision, during collision, and after collision. If I talk about its kinetic energy, you have read about elastic and inelastic collision?
No, sir.
Okay. So if we talk about elastic and inelastic collision, if we talk about elastic collision, kinetic energy remains conserved before collision and after collision, but not during collision. But if we talk about the momentum during collision, you can write this statement: during collision, momentum remains conserved before collision, during collision, and after collision. We can write this statement also. So till now it's okay. We will take the example of this, a bullet example, and we can see. One more important point I'm writing about it. Let's write this. Shall I write this?
Yes, sir.
Okay. Write one note: during collision, the momentum.
So conservation of momentum, that means force is equal to 0, right? Net force.
See, why we are taking this conservation of momentum? See, during collision, when we take the examples of collisions, what happens? Let me draw a picture before. Let's say this is my first object, and this is my second object. I'm calling it m1, and this is m2. This object is moving with some initial velocity u1, and it is moving with some initial velocity u2. And if u1 is greater than u2, what will happen? This object will come and hit this object. Now this is before collision. This is before collision. Okay. Now next case is during collision. This is during collision. During collision, what is going to happen? You can see this is my system. These two particles are in my system. What will happen? This is my first object. This will apply a force on the second object. That is the action, isn't it? This is action. And what will happen? This is the second object. This will apply a force on the first object. This will be the reaction. So this is action. This is reaction. And these two forces are internal forces. There is no external force, because I am considering this as my system. So whatever the forces are there, they are the internal forces. So because of the internal forces, there is no change in the momentum, there is no change in the position, there is no change in the shape of the object. Are you getting? We have already discussed this thing in the second law of Newton's second law of motion. Whatever the changes are there, it is because of the external unbalanced force, isn't it? If there is no external unbalanced force, there is no change. For example, I am having this pen in my hand. It's a solid object, it's a solid material. There are intermolecular forces in it. We have studied in junior classes that solid have intermolecular forces inside them.
Yes, sir.
And it is very strong compared to liquid and gases. So this object is having intermolecular forces in it, interatomic forces in it. So those interatomic forces, intermolecular forces, is not changing its position, it's not changing its shape, it's not changing its velocity, it's not changing anything. Are you getting this thing? Because they are internal forces. Likewise, if I consider this as my system of two particle system, so there is no any external force. If there is no external force, then nothing is going to change. Its shape is not going to change. Its position is not going to change. Its momentum is not going to change. Its velocity is not going to change. Are you getting this thing?
Yes, sir.
Since there is no external force, these forces, whatever they are applying on each other, they are internal forces. Just like this object, there is so many internal forces on it, solid object having, but that is not going to change its position, momentum, nothing. Since the forces are internal forces, this M1 is applying a force on M2 and M2 is applying a force on M1. That is according to Newton's third law, action and reaction. They are internal forces. And they are internal forces, they are not going to bring any change in momentum. So what I can do is, I can use the conservation of momentum, because there is no external force. That means during collision, the momentum of the system will remain conserved before collision, during collision and after collision. Let me write this statement. So this is the situation what after collision. M1, M2, now they are moving with some different velocity, let's say V1 and V2. Okay, so this is before collision, this is during collision, and this is after collision. So this is basically conservation of momentum. So what I can write, during any type of collision, okay, we are having many types of collision, elastic collision, inelastic collision, whatever the collision is. During any type of collision, let me write this, during any type of collision, linear momentum, total linear momentum, or we can say linear momentum of the system, okay, remains constant.
The linear momentum is like?
See, linear momentum is also constant and angular momentum is also constant. Linear momentum, see, when an object is moving in a straight line path, when an object is moving in a straight line path, we call its momentum. That is momentum mass into velocity. We call it linear momentum also, because it is moving in a straight line path. Okay, so the total linear momentum of the system remains constant. That is remains constant before collision, during collision and after collision. Remains constant.
Yes.
Before collision, during collision, or we can simply say remains constant. But this we should understand, that is, it remains, because sometimes when we talk about kinetic energy in elastic collision, kinetic energy remains conserved before collision and after collision, but not during collision. But if we talk about the momentum remains conserved before collision, during collision and after collision.
Yes, sir.
Okay. And after collision. So why it is so? Because there is no external force acting on it. In the system, no external force acting on it. Why it is so? So momentum remains because no external force.
Momentum is acting on the.
Yes,
so
because
momentum is constant.
no external force is acting on the system. Okay, the forces that is acting are only internal forces, and they don't bring any change in the momentum, because no external force is acting on the system. The forces acting are internal forces only. Okay, and they don't bring any change in the momentum. and internal forces only, and they don't bring any change in the momentum. Okay, this is the main idea. And now one more thing is there. If they ask you that is the momentum of, let's say, it can be a system of 2 body particles, or it can be a system of 3 body particles, 4 body particles, or n body particles. Okay, n number of particles. It may be a system of any number of particles. We are considering taking here a 2 body system just to make this thing simple and to understand the basic concept. So now what they are saying, if they ask you is the momentum of this one particle or two, let's say they ask you it's a 2 particle, if I ask you the momentum of this m1, do you think the momentum of m1 is conserved throughout, before collision, during collision, or after collision? Or it is the momentum of the whole system which remain conserved, or momentum of one particle remain conserved?
The whole system.
Yes. It is not the momentum of one single particle. Momentum of one single particle will not remain conserved. For example, the momentum of m1 is not going to remain conserved, or momentum of m2 is not going to remain conserved. It is the momentum of the entire system which is going to remain conserved. Are you getting this thing? If there is a system of n number of particles, or let's say 3 number of particles, 4 number of particles, or n number of particles, if I take one particle, each particle, the momentum of each individual particle is not going to remain conserved. It is the momentum of that entire system is going to remain conserved if there is no external force acting on it. Are you getting this thing? This is the condition. If there is no external force acting on it, then the momentum of that entire system, whatever the number of particles are there in that, the momentum of that entire system will remain conserved. It is not about the momentum of one particle is going to remain conserved. No. Momentum of one particle will change. Okay, because the velocity of one particle may be imparted to the, when it is colliding with the other particle, the velocity of one particle may be imparted to the other particle. Isn't it? It may happen that this object is moving and this object is at rest. And finally, after collision, this object starts moving and this object comes to rest. That means it is imparting its velocity to the other particle, or maybe to the other particle. But what will happen is, the momentum of the entire system will remain conserved if there is no external force. So this is the basic idea. Shall we move now to the next part? Next part, let's take an example of 2 body system. Let's say a bullet and a rifle. And we can explain all these concepts by the help of Newton's third law of motion also. Okay, not of collision but of this gun and this bullet and the gun example. Shall I rub this?
Yes, sir. Yes, sir.
Okay, I'm rubbing this, and now coming to the next part. Now we are having a gun over here. Okay, just like this. We are having a gun. Now the bullet is coming out of the gun going like this. Let's say, let me draw a gun like this. Having a trigger over here. This. So let's try to understand what will happen. What will happen? Let's say we are considering the mass of, let us consider, I am considering small m. Small m as mass of bullet. Okay. Capital M, mass of gun. Okay. Next I am considering U. What is U1?
Initial.
Yes, initial velocity.
Bullet.
Initial velocity of bullet, which will be 0, because initially gun and bullet, they are at rest, and U2 initial velocity of gun. It's okay. And V1 and V2, let's say V1 is final velocity of bullet and V2 is final velocity of gun. These assumptions are okay. Now with these assumptions we are going to understand what is going to happen. See, I am using this thing. I have written over this thing in the bottom M1 U1 plus M2, this thing I am using. With this I will show that the gun will recoil in the backward direction. I am considering this direction as positive. Okay. This whatever the
We have to take sign conventions during
yes,
conservation of momentum.
yes, we have to take sign convention during conservation of momentum. For example, after collision here, if this object starts moving here and this object starts moving here, then this direction will be taken as negative. Okay, this may happen that this ball moves to this direction and this may move to some other direction, or it may move to. If this is collision in one dimension, let's say. This is whatever the example I have written over here, it's a collision in one dimension. But do you think every time the collision will be in one dimension? No. It may happen in two dimension, it may happen in three dimension. So in that case, if the collision is taking place in two dimension, one object will come, let's say there is here I am having one object. Another object will come over here and hit it, and then what will happen? This object may move like this and the other object will move like this. Isn't it? This can happen, na? One object is like this, other object is coming and hitting like this, and after hitting, what may happen? This object may move like this, it will move like this. So in this case, what we are going to do, I told you this thing before, conservation of momentum in two dimension. What we will do, this motion can be considered in two dimension. One along, we will conserve momentum along this direction and we'll make the components of the momentum. Similarly, for this object, we make the components of momentum, one along this direction and one along this direction. And then what we will do, we will compare the components along x-axis before momentum and along y-axis before and after momentum. Just like we are doing, we have written the initial momentum and final momentum. What we will do, we will write the initial momentum along x-axis and final momentum along x-axis. Then we will write initial momentum along y-axis, then along final momentum along y-axis of the system. Then we will equate them and then find out the answer. So that is what we do. Okay. So now let's try to find out. Here I am considering all these things are in one dimension only. Bullet is moving in this direction and gun is recoiling in the other direction. I am considering one dimension only. In two dimension, the only thing happens is we just make the components along x and y axis and make the conservation of momentum along x axis and y axis, and then we solve it. Okay. So if I go by this thing, let's write like this equation. Now what do you think the in gun and the bullet system, if I talk about the gun and the bullet system, what is happening? I am firing the gun and bullet is coming out of it and bullet is applying a force on the gun. This is what is happening. Now in this system, I am considering gun and bullet as my system. There is no external force acting on it. It is just the gun which is applying the force on the bullet, and bullet in turn is applying a force on the gun. This is what is happening. Okay? If gun is applying a force on the bullet, then bullet is going to apply a force on the gun. That's it. And that's why the gun is recoiling in the backward direction. So there is no external force, since external force, F external in this case, is equal to 0. That means momentum of the system remain conserved. That means what? Initial momentum is going to be equal to the final momentum. So this is what we are doing now. So if I write it like this, initial momentum, what I can see, the mass, product of the mass and velocity of gun and bullet, m1 is the mass of this let's say I'm taking it m and u1. This is the mass m u1 plus m u2. This is how it is. U2 is the final initial velocity of the gun. This is how it is. And finally, what I'm getting m v1 plus m v2. This is how it is. But now you see, initially the bullet is at rest and the gun is at rest. Nothing is happening, isn't it? Initially, gun and bullet both are at rest. They are not moving. So put 0 over here. This becomes 0. And finally, what is happening? Once you pull the trigger, what will happen? The bullet will come out. That is the final velocity of the bullet. That we are considering as v1. And as the bullet is coming out, it will apply a force on the gun. The gun will move with a velocity v2, recoil velocity. And from here you can see this initial momentum is 0. Neither gun is moving nor bullet is moving. This equation is 0 on LHS. Now this is what? m1 v1, m v2. Now what I want to find, I want to see that this velocity of gun is in the opposite direction of the bullet. You can see from here. How you can see? This m v2 can be written as, if I take this equation on this side,
minus v
it becomes minus m v1. Now what is the value of v2? It comes out to be minus m v1 divided by m2. Now this means what? If the bullet is moving in the forward direction, then the gun will move in the opposite direction. Okay, this is what we are getting from the conservation of momentum. You can see from the conservation of momentum. And if I apply Newton's third law of motion in it, Newton's third law of motion also says the same thing. Every action has equal and opposite reaction. If gun is applying a force on the bullet, this is the action. The gun is applying a force on the bullet, action. Bullet will apply also the same force on the gun in the backward direction, and the gun will move in the backward direction. You can see from here. You can cross verify these things. Okay? So this is the very basic thing of the momentum, conservation of momentum. And I think and if it is an n particle system, we can use the same result if there is an n number of particle system in this.
Can I just copy it down, sir?
Yes, you can copy it down.
Gun example, can I just copy it down?
Yes, m2 v2, you can copy it down. So this is the very basic concept of this. This is what is happening. You copy it down, then we'll move to the next part. And if we have an n number of particle system, then what we can have is okay.
There is one more thing, sir.
Okay, you can note it down, and then we will come.
Yes. Yes, sir, I'm done.
Okay. So next, if we have a system of n number of particles, let's say we are having only two particles in this collision, and likewise, if we say in a system we are having n number of particles, and that n number of particles, if we are not having any external force in that, or whether they are colliding with each other or they are interacting with each other or whatever may be happening to them, or any other thing may happening to them. So in that case also what will happen, if we are having a particle of n number of system, in that case also, because there is no external force, the initial momentum will be equal to the final momentum. Okay, that means we can write the same results for the n number of particles. Shall I rub this?
Yes, sir.
I am rubbing this and writing the same result for n number of particles. Same result, and they may ask anything about that. And this n number of particles, they may be in one dimensional motion, or they may be in 2 dimensional or 3 dimension. In that case, what we will have to do? We will write the conservation of momentum along x, y and z axis. Okay, let's say for n number of particles, for n number of particles, if the net, see one more thing, net external force. One more thing you need to understand over here, net external force on the system is 0. Then the momentum will remain conserved. Will remain conserved. One more thing we need to understand here is what we have seen, net external force. Suppose we are having a system or n of n number of particles or any number of particles, and some force is acting on it. Okay, and some force is acting on it, and the net force is 0. The net force is 0. Let's say it is a condition of balance force. Then you think momentum is going to remain conserved or it is going to change?
Could you repeat it, sir?
See, there is a system over here, let's say. Let's say I am having a system, one block system, another block system I am having like this, 3 block system I am having like this. There may be some